The Multiverse Employee Handbook has this to say about quantum physics. It is the field of study dedicated to explaining how the universe actually works when it thinks no one's watching. At human scales, the world behaves predictably. Apples fall, clocks tick, and emails remain unanswered. But at the quantum level, everything appears to have given up on consistency entirely. Particles blur into probabilities, energy arrives in discrete packets like cosmic parcel post, and observation itself becomes an act of harassment. The universe, when looked at closely enough, starts behaving like a nervous intern who wasn't told there'd be a performance review. Quantum physics, the handbook explains, began as a well-meaning effort to make sense of light and promptly escalated into a century-long argument about whether reality exists when no one is checking. Some say it does, others insist it's more of a part-time arrangement. Meanwhile, electrons continue orbiting things they shouldn't, occasionally swapping places out of sheer mischief. Philosophers appreciate it for proving once and for all that confusion can be a legitimate career, and everyone else pretends to understand it in polite company, nodding wisely while praying no one asks them to define wave function collapse. The handbook notes that quantum physics has forced humanity to accept several uncomfortable truths. Cause and effect are more like suggestions. Certainty is a social construct, and the vacuum of space is less empty and more quietly seething with infinite potential chaos. In summary, quantum physics is the universe's way of reminding us that it is both deeply elegant and fundamentally unhinged. Everything you think you know is simultaneously true, false, and waiting for further measurement. You're tuned into the Multiverse Employee Handbook. Today we're exploring quantum physics, the science of everything that refuses to stay still long enough to be explained. It's the story of how reality, that supposedly solid, dependable thing beneath your feet, turns out to be a probability distribution with delusions of grandeur. Down in the quantum realm, the universe behaves less like a well-run company and more like an intern with 12 tabs open, half a dozen open Red Bulls on their desk, answering 3 emails at once, and accidentally existing in 2 meetings simultaneously. Particles blink in and out of certainty. Electrons attend every orbit at once. And causality occasionally takes a long lunch without filing the proper forms. The astonishing part, despite all this chaos, the macroscopic world, the one with the traffic lights, tax forms, and sandwiches, somehow emerges from it all, politely pretending to be normal. Because quantum physics isn't a different set of rules for tiny things, it's the same rules, just smaller, stranger, and slightly more sarcastic about our desire for definitive answers. We're now building technologies based on this behavior. Quantum computers that hold calculations in multiple states simultaneously, encryption systems that rely on particles being entangled across distances, communication networks where observing the message changes what it says, which is to say, we've managed to turn the cosmic equivalent of "it's complicated" into a business model. These aren't science fiction proposals, they're engineering projects with budgets, timelines, and increasingly nervous investors. So today we're venturing into the microscopic bureaucracy of the cosmos, where observation changes outcomes, paperwork changes states, and nothing is quite where you left it. But first, gather round the probability distribution, my quantum-entangled colleagues, for a tale that would make even Schrödinger wish he'd stuck with macroscopic pets. In the fluorescent-lit realm of quantum improbability solutions, specifically in the department of definite outcomes, which existed in a superposition of critically important and completely forgotten, the square-haired boss was having what could charitably be called an existential procurement crisis. It had started, as these things often do, with a memo from upper management. The company needed to choose a new coffee vendor. There were two options: Colombian Premium or Ethiopian Select. The deadline was Friday. The decision was allegedly simple, except the square-haired boss had discovered quantum mechanics over lunch. He announced at the emergency meeting, adjusting his tie in the gravitational field of his own certainty, "Gentlemen, I've had a revelation. Why should we choose between these vendors when electrons don't have to choose between paths?" Margaret from procurement looked up from her spreadsheet. "I'm sorry, what?" "Quantum superposition," he said, tapping a trade magazine article he clearly hadn't finished reading. "Particles exist in multiple states simultaneously until observed. Therefore, we shall implement both coffee vendors at once." "Think of the savings," Margaret began. "That's not how I'm authorizing a pilot program. We'll call it the Quantum Coffee Protocol. Dave, calculate the probability amplitude." Dave, from accounting, who'd been quietly hoping to avoid this meeting, reluctantly opened his laptop. "Sir, that's not a financial term. Make it one." Within hours, the initiative had metastasized across departments. Human Resources circulated a memo titled "Inclusive Beverage Practices in Non-Classical States," reminding staff not to collapse the coffee wave function through premature observation. The safety officer installed sensors to detect decoherence events in the break room, which was just a smoke detector with extra labels. Legal drafted a liability waiver for anyone who might experience entanglement side effects, which they defined as confusion, dissatisfaction, or the uncomfortable sensation that your beverage choice is simultaneously correct and incorrect. IT suggested implementing a double-slit experiment with the coffee machine, which was quietly ignored after someone pointed out they'd just be drilling holes in expensive equipment. The implementation date arrived on a Tuesday. 2 coffee urns were placed in the break room, each covered with an opaque lid. One was labeled Colombian, the other Ethiopian. Between them stood a hastily printed sign reading, "Quantum Coffee Protocol active. Do not observe until 3 p.m. Wave function collapse scheduled for end of fiscal quarter." The staff gathered at 2:47. The square-haired boss stood before them like a man who'd discovered fire and was now attempting to franchise it. "Today," he said, "we prove that corporate policy can transcend classical limitations. Behind these lids exist both realities, Colombian and Ethiopian, a superposition of caffeination." Dave ventured carefully. "Sir, I don't think at precisely 3 o'clock we will observe. The wave function will collapse, and we'll have our answer." The seconds ticked by in profound silence. At 2:58, someone's phone buzzed. Several people glanced at it. At 2:59, Margaret sneezed and accidentally bumped the Ethiopian urn.
"I'm sorry."
At 3 o'clock exactly, the square-haired boss lifted both lids with ceremonial gravity. Both urns contained lukewarm water with a faint smell of disappointment. No coffee, no grounds, just liquid that had clearly never made any definitive commitments about its identity. "Ah," said the square-haired boss after a very long pause, "quantum mechanics has betrayed us." Margaret offered gently, Or someone in facilities misunderstood the work order and just filled both with tap water. That's what I said. Quantum betrayal. He cleared his throat, adjusted his tie, and addressed the room with all the dignity of a man whose LinkedIn profile still listed Microsoft Office under his skills. We'll form a committee to study the implications of measurement on beverage selection. Dave, draft the charter. Margaret, investigate whether we can expense this as R&D. And as the staff dispersed back to their desks, slightly confused, deeply thirsty, and no closer to having functional coffee, the square-haired boss stood alone in the break room, staring at 2 urns of tepid water. Somewhere in the quantum foam of possibility, there existed a universe where this had worked. He just wasn't sure how to get there from here, or whether that universe had better funding. And that brings us to the fascinating science behind quantum physics. Unlike the square-haired boss's coffee experiment, this actually works when you understand the rules. First, some terminology. Because physicists love making simple things sound complicated, quantum physics is the overarching field. It's the study of how nature behaves at the smallest scales. Within it sit several sub-disciplines. Quantum mechanics, which describes how individual particles behave. Quantum field theory, which describes how fields and particles interact. Quantum electrodynamics, quantum chromodynamics, and several others with equally intimidating names. For today's purposes, we're focusing primarily on quantum mechanics, the rule book for how individual particles operate when no one's looking, and occasionally when they are. The central revelation of quantum mechanics is superposition. Imagine a coin, heads or tails. Simple binary choice, very sensible, very classical. Now imagine a quantum coin, what physicists call a qubit. It can also be heads or tails, but here's the difference. It can also be both. Simultaneously, not we don't know which, but genuinely both at once. It can be 30% heads and 70% tails, or 40-60, or any combination you can mathematically describe. This isn't a coin spinning in the air where we just haven't looked yet. This is a coin that genuinely exists in multiple states until the moment you observe it. Real particles behave this way. Electrons, for instance, have a property called spin, up or down, like heads or tails, and they can exist in superposition, partially up and partially down simultaneously. The key insight that confuses everyone, including the physicists initially, is that these probabilities are fundamental to nature. They're not there because we lack information. They're woven into how reality operates. When we say there's a 50% chance of rain tomorrow, that's because we don't have perfect knowledge of atmospheric conditions. It's going to rain or it's not. We just don't know which yet. Quantum mechanics doesn't work that way. The electron genuinely is in both states. The probability isn't ignorance. It's the actual configuration of reality before measurement. And the proof? An experiment so elegantly simple it fits in a single room, yet so philosophically disturbing, it's kept physicists arguing for a century. It's called the double-slit experiment, and it demonstrates beyond reasonable doubt that particles don't just take one path from point A to point B. They take every possible path, simultaneously. When we return, we'll explore exactly how particles manage this feat, what happens when we finally observe them, and why the universe appears to be running on a probability engine that somehow produces a mostly reliable macroscopic world. We'll also discover why companies are investing billions in quantum computers. Machines built on the principle that if reality operates in superposition, we might as well exploit it for computational advantage. Welcome back, my deterministically challenged colleagues. So, how do we know particles actually explore multiple paths simultaneously? How do we know superposition isn't just a mathematical convenience? The answer comes from an experiment so simple it's almost insulting, yet so philosophically disturbing it's kept physicists arguing for a century. The double-slit experiment. The setup, an electron gun that fires single electrons. A barrier with two narrow slits cut into it. A detector screen behind. Fire electrons at the barrier. If electrons behaved like classical particles, tiny billiard balls, you'd expect two bright spots on the screen, one opposite each slit. Like throwing tennis balls at a wall with two openings. But that's not what happens. You get stripes, an interference pattern, alternating bands of many electrons and almost none, many, none, many, none. This is the pattern you get from waves. Water waves passing through two gaps spread out, overlap, interfere. Peaks meet peaks, reinforcement. Peaks meet troughs, cancellation. So perhaps electrons are waves after all? Here's where it gets truly unsettling. Slow the electron gun down. Fire one particle at a time. Wait for it to hit the screen. Fire another. Wait. One electron, one detection, one tiny dot. Surely now you'll get those two classical clusters because each individual particle has to go through one slit or the other. Doesn't it? It does not. The interference pattern still builds up gradually, one electron at a time, each landing in a position that collectively recreates those same mysterious stripes. Each individual electron is interfering with itself, which means it didn't go through the left slit or the right slit. It explored both paths simultaneously, and not just both slits. As we'll see, it explored every geometrically possible route between emission and detection. This has been confirmed thousands of times since the early 20th century, with electrons, photons, neutrons, with entire molecules. In 2023, researchers in Vienna managed it with molecules containing over 2,000 atoms. The conclusion is unavoidable. It's rather like filing an expense report that simultaneously travels through every possible approval chain. Finance, management, legal, that one person who's technically retired but still has signing authority, exploring all bureaucratic paths at once until someone actually opens the email, at which point it collapses into whichever route causes maximum delay. The physicist Richard Feynman, and I'm paraphrasing his lectures here, described this experiment as containing the central mystery of quantum mechanics. He suggested that any other quantum situation could be understood by referring back to it. He also developed an elegantly simple method for calculating what happens. For every possible path the electron could take from gun to screen, and I mean every path, through the left slit, through the right slit, looping around the laboratory, taking an improbable detour via the Andromeda galaxy, you assign what's called a complex number. Think of it as a little clock face. Each path gets a clock hand pointing in some direction with a certain length. You calculate how those clock hands evolve as the particle travels along each route. Then, for any point on the detector screen, you add up all the clock hands from every possible path to that point. Where the hands align and reinforce each other, high probability of finding the electron. Where they point in opposite directions and cancel out, zero probability. This is how you get interference. Paths literally canceling each other out mathematically. The mathematics are straightforward. First-year physics students learn these calculations. The predictions match experiments to extraordinary precision. Simple prescription for calculation, profound implications for reality. Because the question remains, does the electron really take every path? Or is this just convenient mathematics that happens to produce the right answer? Most physicists today would say it genuinely does explore every route. This isn't computational sleight of hand. This is what nature actually does when particles travel from one place to another. And here's the final twist. If you modify the experiment to detect which slit the electron passes through, install a little sensor that tells you left or right, the interference pattern vanishes instantly. You get two boring classical clusters opposite the slits. The act of observation doesn't reveal a pre-existing answer. It forces reality to commit to a definite state. The universe, it appears, runs on a probability engine that only produces definite outcomes when directly interrogated. If particles existing in multiple states simultaneously wasn't sufficiently disorienting, quantum mechanics offers a second phenomenon that suggests the universe never properly read the manual on personal boundaries. Take two particles. Make them interact in particular ways. They become entangled, which is the polite scientific term for what happens when two quantum objects refuse to maintain separate paperwork. The particles now share a single quantum state, not similar states. One state, jointly owned across arbitrary distances. Measure the first particle. It resolves to some definite value. Let's say up. The second particle, which could be orbiting Saturn at this point, is instantly down. Not probably down, definitely down. Not because a signal traveled between them at light speed, but because the measurement forced both particles to finally commit to individual values they didn't previously possess. In 1935, Albert Einstein identified this as philosophically unacceptable. He and colleagues published a paper arguing that quantum mechanics must be incomplete. Hidden variables must exist, he insisted, that predetermine the results. Otherwise, particles would be affecting each other instantaneously across space, which struck him as the sort of thing a well-organized universe simply wouldn't permit. He called it spooky action at a distance, deploying the technical term for "I dislike this immensely." The universe, for its part, continued operating exactly as before, untroubled by Einstein's aesthetic concerns. Experiments throughout the late 20th century confirmed there are no hidden variables. The particles genuinely lack individual states until measured. In 2022, a Nobel Prize was awarded for proving this conclusively. Which means Einstein, possibly the most famous physicist in human history, spent decades being bothered by a feature of reality that turned out to be correct. One might observe that humans routinely invest considerable energy determining what the universe should and shouldn't do, only to discover that nature has not, in fact, distributed the survey asking for opinions. Having learned that particles can exist in superposition and maintain correlations across galactic distances, humanity's immediate response was to ask whether this could simulate protein folding, because we'd like to cure diseases, but mostly we'd quite like to win a Nobel Prize. The reasoning is sound. A classical computer uses bits. Each bit is 0 or 1. 2 bits give you 4 possible combinations, but you can only hold one combination at a time. A quantum computer uses qubits in superposition. 2 qubits can represent all 4 combinations simultaneously, 3 all 8 at once. The scaling is exponential. 100 qubits can hold 2 to the 100th power states. A number so large that if you wrote it out in atoms, you'd need multiple solar systems worth of matter. 500 qubits exceed every atom in the observable universe. And humans are attempting to build this inside a box in a laboratory. Admittedly, a very expensive box kept colder than the vacuum of space, but still, a box that fits in a room that humans can theoretically point at. The ambition is to perform calculations that classical computers would require longer than the current age of the universe to complete. Drug design by simulating quantum molecular interactions, code breaking by testing billions of combinations simultaneously, financial modeling, climate simulation, materials engineering at the atomic scale, fantasy football predictions.
Wait, what?
These are not modest goals for a species that only recently stopped using sticks to hunt mammoths. The difficulty is maintaining quantum coherence. Quantum states are fragile with a thoroughness that borders on malicious. Room temperature destroys them. Vibration destroys them. Electromagnetic radiation destroys them. Cosmic rays passing through the building destroy them. A graduate student dropping a pencil 3 floors up can theoretically destroy them.
Oops.
Current quantum computers operate at approximately 15 millikelvin. For context, the coldest naturally occurring place in the solar system is considerably warmer. Interstellar space is warmer. The cosmic microwave background radiation left over from the Big Bang is warmer. Humans have built refrigerators that achieve temperatures lower than anywhere else in the known universe, specifically to prevent qubits from noticing their surroundings. The machines cost tens of millions of dollars. They require liquid helium, dilution refrigerators, electromagnetic shielding, vibration isolation, and several dozen scientists who've committed their careers to keeping a small number of qubits sufficiently cold and undisturbed that they maintain superposition for the few microseconds needed to perform calculations. And they work. Not reliably, not for most problems, but for certain specific quantum simulations and optimization tasks, they can achieve results classical computers cannot replicate in reasonable time frames. We are essentially at the stage where we've discovered that if you cool a device to temperatures found nowhere naturally in our corner of the galaxy, isolate it from reality itself to the greatest extent possible, and ask it extremely particular mathematical questions in precisely formulated ways, it can exploit quantum superposition to solve otherwise intractable problems. This is being described as revolutionary technology, which it is. Humans have historically excelled at finding improbable phenomena in nature and hammering them into useful tools without fully understanding why anything works. We learned to harness fire before understanding combustion. We bred crops before discovering genetics. It's a species-wide strategy. Exploit now. Comprehend later. Argue about interpretation indefinitely. The universe provides the mechanisms. Humans build machines, and nature remains indifferent to our confusion. Well, my probabilistically inclined colleagues, we've reached the end of another quantum staff meeting with reality itself. Today we've learned that quantum physics isn't a different set of rules for tiny things. It's the same rules, just smaller, stranger, and considerably less apologetic about making no intuitive sense whatsoever. We've discovered that particles exist in superposition until measured, explore every possible path simultaneously, and can remain entangled across galactic distances in ways that bothered Einstein for decades, but which the universe found perfectly acceptable. We've also learned that humanity's response to discovering the fundamental weirdness of reality was to immediately ask whether it could be cooled to near absolute zero and persuaded to optimize supply chains, which is, admittedly, very on-brand for a species that never evolved to understand quantum mechanics, but decided to build computers exploiting it anyway. Somewhere in the quantum foam of possibility, there exists a universe where the square-haired boss successfully implemented the quantum coffee protocol, where particles behave sensibly, and where observation doesn't collapse wave functions into the least convenient outcome. We simply don't inhabit that universe. We inhabit this one, where reality runs on probability distributions, where measurement changes outcomes, and where the most sophisticated technology humanity can build requires keeping things colder than interstellar space just to prevent them from noticing their surroundings. Want to explore more quantum corporate chaos? Visit us at multiverseemployeehandbook.com. And if you've enjoyed today's journey into the microscopic bureaucracy of the cosmos, share it with a fellow deterministically confused colleague. Perhaps someone who still believes reality makes sense and could benefit from some corrective information. Spread our signal like a wave function through configuration space, or failing that, just send them the link. This is your quantum coherent correspondent, reminding you that in the multiverse of quantum possibilities, we're all just probability amplitudes, waiting for someone to observe us. At which point, we'll collapse into whatever state requires the most paperwork. And according to the latest memo from the Department of Definite Outcomes, next quarter's budget has been approved, denied, and lost in processing simultaneously, and will remain in that state until someone from finance actually opens the email, at which point it will resolve to whichever option causes maximum administrative confusion. And as physicist and science communicator Brian Cox once stated, there aren't different rules for the quantum world and the everyday world. It's the same rules all the way through. Which should be comforting, except it means that the reason my earbuds are never where I left them isn't actually quantum superposition. I'm just disorganized, and I can't blame fundamental physics for my personal failings. Hello?
Hey, I'm Rob Corrigan, the human who dreamt up the Multiverse Employee Handbook, because I can't stop marveling at how strange and wonderful the universe is, and how often it behaves like a very large company with confusing corporate policies. In a world increasingly run by AI, I think it matters to be clear about what's human made and what's conjured by machine magic. So here's the straight up rundown. The host, David, is a professional voice actor. The voice you hear has been digitized using 11 Labs voice cloning technology, with his blessing and excellent enunciation. The episode thumbnails are created with OpenArt's AI models. Music and sound effects come from Pixabay, composed by human artists. Everything else, the writing, the jokes, the research, is 100% me, human hands, human brain, and occasional human muttering. Thanks for listening, and for being a good human in an increasingly automated cosmos. And if you like this show and make it this far, it would really mean a lot to me if you shared it with a colleague, a friend, or anyone. It's really the best way to make podcasts like this grow, and I sincerely appreciate it.
Rob, do stop ringing after hours. The kettle's on and I'm halfway through a biscuit. Toodaloo.